Welcome children in this third video on the concept of force. In this video, we will talk about principle of moments and we will discuss the verification of the principle of moments. When several forces act on a pivoted body, they tend to rotate it about an axis passing through the pivot. The resultant moment of all the forces about the pivoted point is obtained by taking the algebraic sum of the moment of each force about that point. To find the algebraic sum, the anticlockwise moment is taken positive, while the clockwise moment is taken as negative. According to the principle of moments, if the algebraic sum of moments of all the forces acting on the body about the axis of rotation is 0, the body is said to be in equilibrium. Thus, we can say that in equilibrium, sum of clockwise moments is equal to sum of anticlockwise moments. So, children, a physical balance, what you call as beam balance, it works on the principle of moments. Now the question arises, how to verify principle of moments? So kids, I'm just going to explain it and then we have a video followed by this clip. I think it will make you understand better. So suspend a meter rule. When I say meter rule, I hope you understand 100 centimeter scale horizontally from a fixed support by means of a strong thread at O as shown in figure. Now suspend two spring balances A and B on the meter rule on either side of the thread. Suspend some slotted weights W1 and W2 on the spring balance. The meter scale may tilt to one end. Now adjust either the slotted weights on the spring balance or the position of the spring balance on either side of thread in such a way that the meter rule again becomes horizontal. Let the weight suspended from the spring balance A on the right side of the thread, B W1 at a distance OA that has been marked as L1, while the weight suspended from the spring balance B on the left side of the thread be W2 at a distance OB which has been marked as L2. The weight W1 tends to turn the meter rule clockwise, while the weight W2 tends to turn the meter rule anti-clockwise. So, the clockwise moment of weight W1 about point O will be given by W1 into W2 and anti-clockwise moment of weight W2 about point O will be given by W2 into L2. So in equilibrium, when the meter rule is in horizontal position, we will find out that W1 into L1 is equal to W2 into L2. That is, clockwise moment is equal to anti-clockwise moment. So this verifies the principle of moments. Now let's watch a video to understand it in a better way. Hello children, we are going to start with the practicals. And the very first practical is related to your very first chapter, that is force. So kids, if you remember, we have done principle of moments. I'm just giving you statement again. That is, sum of clockwise moments is equal to sum of anti-clockwise moment in equilibrium. I'm repeating, in equilibrium is the keyword, right? So this is the setup to prove principle of moments. For that we are using a meter scale, right? A known weight is there. And how come this is known weight? It is written there. If you check out, it's written here. It is weight. So it is 20 gram force. It is not 20 gram because gram is for mass, right? We are talking about weight. And as I've already told you, principle of moments is applicable for weight. Even if in numericals you get it, you have to convert it in gram force or kgf. And this is the unknown weight. I want to find out the weight of this metallic bomb, right? So how we are going to proceed? This is your meter scale, right? And since it's a symmetrical object, so I am aware where the CG is going to lie. So if I'm telling you this is meter scale means 100 centimeter. So I think you can make out, actually I should be getting it at 50 centimeter as the CG. Okay, let's see whether we are getting it or it is something else. And if it is something else, then why it is something else? Because theoretically we have learned that the symmetrical objects, for symmetrical objects, the CG is exactly the geometrical center. So I'm trying to adjust it. I'm trying to adjust the scale at 50 because we know that at CG we are able to balance the body. Sometimes you have your 15 centimeter scale. You try to balance it on your finger and you're able to balance it. You can try it at home, right? So this is, but if you check out here, I'm not able to balance it because it is swinging. It is given you which moment? Can you tell me? This is your clockwise moment. And if it is swinging this way, this is giving me anti-clockwise moment, right? This is giving me anti-clockwise moment. It means, again, I need to shift the position so that I am able to balance it. Again, it is giving me clockwise. It means, again, I need to shift. I need to shift. Again, I need to shift. I think it is balanced. Care should be taken because nothing should be supporting the meter scale, right? Nothing should be supporting. And if you check out here, 2 threads are there. You have to make it sure that every time you use the same thread as your reference point. Means if I'm going to take reading using the first thread, it should always be first thread, or it can be second thread. It's up to you, right? So this is how I'm going to balance it. Now it's giving me clockwise moment, right? So here again I'm balancing, it's giving me clockwise. Again I need to shift. Again I need to shift. This is how I'm going to balance it. I think I'm able to. Yes, and it's coming out to be 49.5, 6, 7, 8, 9. It is coming out to be 49.9, not exactly 50. What could be the reason? The reason is because the scale may be uneven. You can find out here actually at few places it's not regular, right? And it may be that dust is there and it is just sticking to the scale, and it may be the one of the reason. I mean, rather I've given you 2 reasons, right? So now what is to be done? I want to find out the weight of this unknown weight of this object, and I'm going to hang it on the right hand side. Known weight is to be hanged here. Now suppose I decided to hang it at 30 centimeter. Now what is my job? It is just like a beam balance. Suppose you have a weight, right? Now what is your job? You have to balance it in such a way, weight is fixed. I can't change the weight, right? But I can change the length, right? Can you see it is giving me clockwise moment? It means I have to adjust it in such a way that can you see? It's almost done. It's almost done. I think it's almost done, right? So now what is to be done? See here, what is the effective length here? Sum of clockwise moment. This is your clockwise moment. This is my known weight, 20 gram force. And what is the effective length? I need to subtract it from CG, if you remember. This is 49.9 and this is 30 here. So what is the effective length? It is 19.9 centimeters. And what about this? W2 is not known to me, right? This is what I have to find out. And what is the effective length here? This is 65. This is 65 and this is I think 49.9. So if you substitute it in the formula, you remember the formula of principle of moments? W1 L1 is equal to W2 L2. W1 L1, W2 L2. So this is the unknown quantity that I have to find out, and other 3 quantities are known to me. So this is how we find the weight of this object given to me using principle of moments. Now this is the first reading. Then how to have the second reading? Second reading is just change the place. Just Suppose it was 30 before, now let it be 20 now, right? And now again I have to adjust. Again I have to adjust in such a way that it gets balanced, right? And I think it is balanced, maybe because of this support, yes. Again I have to work in such a way that it gets balanced. And if you check out, this is the way. Sometimes it gives you swing. The best thing is to just hold it like this so that it don't move. And I think it is again balanced, right? So again, W1 is known to me. Just find out L1. Again it is 20, 49.9 means 49.9 minus 20. And this is W2, I have to find out. And again this is L2. This is, I think this is 72.5 or 4, right? Just subtract it from the, subtract CG from 72.4, yes, I think 4. And then you just substitute it in the formula, and this way you will be getting the answer. So this is how you are going to work from principle of moments. Thank you. I hope so. The video has made your understanding better. And I think now you will be able to answer how come an elderly person sitting on one side of the seesaw and a kid sitting on the other side of the seesaw are able to balance each other. It is only the distance from the pivot that makes a difference. So, from this principle of moments, we have learned that W1 L1 is equal to W2 L2. We need to remember that here it is W1, that is the weight of the body, and not the mass of the body that is applicable for principle of moments. So kids, thank you for watching, and let's wait for the next video to have more concepts. Take care. Bye-bye.